All right, our next topic that deals with differential equations is called second order linear differential equations. And what that means is the second part means you have a second derivative that's involved in the differential equation. You might even have a first derivative involved, and you might have a y term involved. That's all possible. Linear because second derivative is just to the first power, first derivatives to the first power, and y's to the first power. Okay? Let's see. In the most general form, what you might have in front of the y double prime is some function, continuous function of x. The same thing, you might have another continuous function of x in front of the first derivative, the y prime term. You might have another continuous function or expression in x in front of the y, and you could have some continuous expression or function of x on the right-hand side too. All right. Then you get into a little bit more specific second-order linear differential equations. They would be considered homogeneous if the right side is 0. So the g of x in this case would be 0. And that's the case we're going to look at here in this video. You could also have this g of x not be 0, and that would be the non-homogeneous case. All right, and then we're going to break it down even further. Instead of these, the p of x, q of x, and r of x being expressions in x, we're going to look at what happens when they are just constant coefficients. So in other words, the p of x is going to be some number a, q of x is going to be some number b, and r of x will be some number c. All right, so here's the type of second order linear homogeneous differential equation we're going to look at here. Something in like an a double prime of y plus b y prime plus cy equals 0. All right, and in order to figure out the solution, what you really do is you're going to set up what's called a characteristic equation. So what is a characteristic equation? We take the coefficients in front of the second derivative, first derivative, and y, and we put them in front of an r squared and r, and just put the coefficient in front of the y as c in this case here. And we form a quadratic equation in r, all right? And r will be the roots or the zeros or whatever of this characteristic equation. And depending on the values of r, it will lead to the general solution. And then if we have any initial conditions, we can find a particular solution. So what you'll do is you'll take the coefficients in front of the second, first, and y, second derivative, first derivative, and y, form this characteristic equation, set it equal to, it will be equal to 0, and solve for r. If you get two r values that are real, which means real numbers, and they are distinct or different, then your general solution to that differential equation will be y is equal to some coefficient we'll call c sub 1 e to the r sub 1 x, and r sub 1 is one of the roots to the characteristic equation, plus c sub 2, some other coefficient, e to the r sub 2 x, where r sub 2 is the other distinct root. All right, and then define the c sub 1 and the c sub 2's. If you had initial conditions, you could do that. All right, but that's the form of this general solution. If you find that your roots, whenever you solve this characteristic equation, are identical, so r sub 1 and r sub 2 are the same, we just call them r, because they're identical, then your general solution looks almost the same as the one right above it, except your r's are the same, and the second term has an x also in it, so it would be c sub 2 x e to the rx. All right? So that's what you would get for the general solution. And again, to find your c sub 1 and c sub 2, you would need some initial conditions. If and this is the third possibility, your roots, your R values, your R sub 1, your R sub 2, if they end up being complex, so you're going to have, a square root of a negative number or something like that. So one we'll call alpha plus I beta, and the other one we'll call alpha minus I beta. If that's what you get, then your general solution will look like this. Y will be equal to e to the alpha x, whereas alpha is the kind of real part of the complex root, not the part that has the I in it, multiplied by parentheses c sub 1 cosine of beta, where beta is the coefficient in front of the I, or in this case behind the I, x, plus c sub 2 sine of beta, same beta, x here. All right? And the particular solutions, again, would be found when you can figure out what c sub 1, c sub 2 are based on initial conditions or initial values. All right? Okay, so let's take a look at an example. So you're going to really refer to this little chart here depending on what your roots end up being. Are they real but different? Are they real but the same? Or are they complex? Okay, so the first differential equation we'll look at here is y double prime plus y prime minus 6y equals 0, and we have two initial conditions. The first one is that y will be 1 when x is 0. The second one will be that the y prime, the first derivative, will be 0 when x is 0. All right? So it's already set up in the nice form where we have the y double prime term, the y prime term next, the y term next, and 0 on the right side. So a is 1, b is 1, and c is negative 6. So I have 1r squared plus 1r minus 6 equals 0. This factors on the left side into r plus 3 times r minus 2, okay, equals 0. So one of the r's, we'll call it r sub 1, would be negative 3. The other one would be, we'll call it r sub 2, is equal to 2. All right, so we found that. So we have two that are real but distinct. So if they are real but distinct, then our general solution will take this form here, okay? And that's what I've got right down into here. So here's the general form for that one, general solution. We're going to plug in our r sub 1, r sub 2's into the appropriate places. So now you have the general solution. Y is equal to c sub 1 e to the negative 3x plus c sub 2 e to the 2x. All right? But we do have some initial conditions here. So let's pull the first one down here. Y is 1 when x is 0. So I'm going to plug that into here to try to figure out what c sub 1 and c sub 2 are. So y is 1, there's the 1, when x is 0. So I'm going to have c sub 1 e to the 0. Well, e to the 0 is 1, so I get c sub 1 plus c sub 2 e to the 0, because x is 0. E to the 0 is 1, so I get c sub 2. So I don't really have enough information yet to figure out what c sub 1 and c sub 2 are. All I know is that when I add them up, they have to be equal to 1. So let me try to use this second initial condition. All right, to use this condition here, I need a first derivative. Well, I know y is this so far. So let me take the derivative of my kind of general solution right now, and then I can plug in this initial condition here. So y prime is equal to, I'm going to take the derivative of the first term here. So it's going to be c sub 1, which is just some number. I'm going to figure it out. The derivative of e to the negative 3x is e to the negative 3x times negative 3. So that's why when I take the derivative of this first term, I get negative 3 c sub 1 e to the negative 3x. I'll take the derivative of the second term up here, and I'll get c sub 2 e to the 2x times 2, because the power up here was more complicated than x, so I have a chain rule. All right? So we'll make that plus 2 c sub 2 e to the 2x. So here's the derivative. Go up, grab this condition here that y prime is 0 when x is 0. And now I'm going to plug that in. So y prime is 0, so this is 0 when x is 0. So I get negative 3 c sub 1 e to the 0. Well, that's a 1, so I get negative 3 c sub 1 plus 2 c sub 2 e to the 0, which is just 2 c sub 2. So what does that mean? I still don't know what c sub 1 and c sub 2 are, but they have another relationship here. That, along with their relationship up here, really becomes two equations and two unknowns, and I can solve it any way I want. Substitution, elimination, whatever. I decided to do elimination. So I'm going to take the second of these two equations that have c sub 1 and c sub 2 in, write it down here. I'll take the first one, write it down here, and I'm going to use elimination. So I'm going to multiply the second equation by 3. So get 3 equals 3c sub 1 plus 3c sub 2. I'm just kind of writing it like this. And then I'm going to add the top equation and the bottom equation after I've multiplied it by 3. So I get 0 plus 3 times 1, so I get 3 over here. I'm going to get negative 3 c sub 1 plus 3 c sub 1. The c sub 1's canceled. They've been eliminated. Then I get 2c sub 2 plus 3 c sub 2's gives me 5c sub 2's. So now I get 3 is equal to 5c sub 2. Solve for c sub 2. It's going to be 3/5. And then I'll plug it into any equation I want. I'm going to plug it into this one right up into here. And I'll find that c sub 1 is 2/5. So now that I have those things, I go to my general solution here where I didn't know c sub 1 and c sub 2 and plug in their values now. And I get the particular solution right here. Y is equal to 2/5 e to the negative 3x plus 3/5 e to the 2x. And that is our particular solution to this second order homogeneous linear differential equation right here. All right? Okay, we got one more problem to look at, example problem, but I'll put it on the next video.